Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This is the final video on graphing sine and cosine functions. You should have watched every video in the series if you're brand new to trigonometry. It is critical that you know all that stuff. I know I use that word a lot, critical, right? But it is kind of important. So let's talk about the topics that you could see with applications involving sinusoidal functions. By the way, I say sinusoidal and I never told you why. Sinusoidal functions are functions defined by sine and cosine curves. There you go. They're oscillatory functions. So here's the definition of simple harmonic motion and frequency. Any object or quantity moving with a periodic sinusoidal oscillation, just means sine and cosine, of the form a sine of omega t or a cosine of omega t, where a and omega are constants, is said to exhibit simple harmonic motion. The frequency of this motion is defined to be 1 over the period, and it represents the number of cycles or oscillations per unit time. Now, you deal with, or see, or hear, I should say, simple harmonic motion all the time. Now, maybe it's not so simple, but sound waves. Sound waves are simple harmonic motions. And it's just because they have, well, they're decaying harmonic, but that's okay. Anyhow, they have a certain number of cycles per second, and that would be the hertz. That's what a hertz is, a number of cycles per second, specifically 1 cycle per second, as you can see below. So it is important that we kind of talk about this. Also, if you turn on the radio, the frequency is actually, the FM, frequency modulation, is actually sinusoidal frequency. So this is around us all the time. This is incredibly important for electrical engineering, engineering in general, physics, all this stuff. So this is really deep material. Don't be intimidated by the use of omega here. It's the same thing as B. Just, it's common that people use omega though, but it's the same thing as B. So don't really freak out about that. All right. So let's go ahead and do an example so we can kind of understand this and not be so intimidated by it. A mass attached to a spring is pulled downward and released. The displacement of the mass from equilibrium position after t seconds is given by the function d, displacement, equals cosine of omega t, where d is measured in centimeters. When it is shortest, the spring's length is 8 centimeters and 16 centimeters when it is most extended. If the spring oscillates with a frequency of 1.2 hertz, find d as a function of t. That sounds like a terrible sounding problem, right? But it's actually not too bad. We have some block attached to a ceiling, and we have a spring attached to that block. The spring would look something like this, right? And the natural length of the spring is what it would be prior to being compressed or being extended. But somebody has extended this. So they add on a little more distance there. They pull it down a little bit further, and then they let go, and it starts oscillating. Rising and falling, rising and falling, rising and falling, rising and falling. Now, something to note here. In physics, it is very common to consider the downward direction to be positive and the upward direction to be negative, which is a very big frustration for students the first time they see this. A massive frustration. So just to let you know, that is going to be the case that we're going to deal with in this problem. But you get kind of used to that. It's because really gravitational pull and you don't want to deal with a bunch of negative numbers all the time. So when you deal with gravity, you assume it's pulling it down, and that we're going to call that the positive direction. If it was going upward, some force has to act on it to push it up, and so it's going in the negative direction. It's more work to push up. So that's just a heads up. All right, so let's see. When it is shortest, the spring's length is 8. I'm going to just mark that on here. And when it's longest, the spring's length is 16. So therefore, the midline is halfway between those two values. The midline here is, let's see, 16 plus 8 is 24, divided by 2 is 12. Now, also I should note, so this midline happens at y equals 12. I should note that my numbers are upside down as well. Notice that. I went from 8 on top to 16 on bottom, which matches, by the way, the arrow direction. Negative is up, positive is down. So it is going like that. However, it is rare that you really care about the midline in these problems. You only use that to find the amplitude of the oscillation. And the amplitude of this oscillation is the distance between the midline, mark that here, and either the minimum or the maximum. In this case, we'll just use the minimum, but it's the same number either way. The amplitude is 4. So I happen to know that our cosine function, which they kind of in this problem misled us a little bit, it's d equals 4 times the cosine of omega t. We're not done with it, but just letting you know that the amplitude on this cosine function is a 4. We're not going to worry about the plus 12 because that is not part of our problem. They really should have written it with an amplitude in front of that. But the midline is never really considered in a physics problem. Nobody really cares about that. What we care about is the oscillatory nature of it. All right, so let's see what else they gave us. Shortest is 8, most extended is 16, got that. And they tell us the frequency is 1.2 hertz. Let me write that down over here. The frequency equals 1.2 hertz. Now remember, the frequency is 1 over the period. So it's the reciprocal of the period. So that implies that the period of our cosine function should be 1 over 1.2, which is, if you multiply top and bottom by 10, 10 twelfths, which reduces down to divide by 2, 5/6. It's just much easier to write it that way, I think. So our period is 5/6. And remember, that's kind of acting like a b in front of our x, even though it's a t and it's an omega. I get it. So, and we know that the period is 2 pi over b. So I'm going to solve that equation. Multiply both sides by b. Multiply both sides by 6. Divide both sides by 5. 12 pi over 5. So that's what our value of b is. Even though they didn't give us a b, I'm calling it b just to really kind of keep consistent, right? So now we're going to go ahead and sub that in for, again, what I said was b. That's 12 pi over 5. So d, our function for displacement, is 4 times the cosine of 12 pi over 5. Let me write that this way. 12 pi over 5. And then times t. Don't forget that t is there. That's the variable you need there. Now, I've actually graphed it off to the side here. Let me just open that up to show you. So this is 4 times the cosine of 12 pi over 5. And remember, this is going to be upside down, honestly. It's upside down. So imagine that here's the block, and we pulled the stretch of spring out to this, and we're letting go. It's going to start oscillating. Here we go. So the spring is oscillating. This is just showcasing right here in red the oscillatory nature of the object floating back and forth. And the black dot is actually carving out the cosine curve over time. But really, the spring is just showcasing like this. So very nice. Good representation of simple oscillatory motion. Now this one, I'm trying to squeeze as much as I can out of it. If you've watched my videos throughout the series, I've probably used this 2, maybe 3 times so far. because it's real. The London Eye is a Ferris wheel on the south bank of the River Thames in the borough of Lambeth. It was the world's largest Ferris wheel from 1999 until 2006, when it was surpassed by the Star of Nanchang in Nanchang, China. The diameter of the London Eye is 394 feet, and passengers enter into the wheel's capsules at an elevation of 30 feet from the street level. The eye makes one full revolution every 30 minutes. Find an equation that gives a passenger's height above the ground at any time t during a ride on the London Eye. Well, let's go ahead and take a picture or showcase actually, here's a picture of it right here. So let's see if I can show it. Yeah, I can. Okay. So if this is the ground level, they enter in at a height of 30 feet. So there's a 30-foot elevation they start at. And then it just starts to go up and around. And their height can be given if you just think about it this way. Here's the ground. They start at a height of 30. They go up and then down. There you go. So you can see it's an upside down cosine curve. That would be, with respect to time, this would be their height. Okay. So let's go ahead and figure out a function for this situation. We happen to know that it does a full revolution every 30 minutes. So the period of this function is 30 minutes. All right. And let's see what else. Well, we know the diameter. They gave us the diameter of this to be 394 feet. So the radius is half of that. And half of 394 is 197. So I'll write that in there, 197 feet. So we happen to know that from the lowest low to the midline would be 197 feet. So this midline must be at 30 plus 197 or 227. And that gives us an actual equation for the midline, y equals 227. We also know the distance between the midline and either the minimum or the maximum. That's the radius. It's 200 or 197. We pretty much have everything we need to write down a function for this person's height at any given moment. Remember the height, well, this looks like a negative a cosine of bx plus c plus d. And a is the amplitude, and we just said that's 197, so let's fill that in. I don't like the red ink. Let's go with black ink. Negative 197 cosine of bx plus c plus d. B is associated with the period. Remember, the period here is 30. I'll write that in here. Period is 30 minutes, which is equal to 2 pi over b. Multiply both sides of that block by b and divide by 30, and you find that b is equal to pi over 15. So we'll go ahead and write that in. This is negative 197 cosine of pi over 15 x plus c plus d. Notice this cosine curve is not shifted left or right. Its initial point here is at 0, 30. So, since it hasn't been shifted, c is 0. There's no horizontal shift. So we have negative 197 cosine of pi over 15 x plus d. And d is just our midline shift, which is 227. So let's go ahead and write that in. Negative 197 cosine of pi over 15 x plus 227. One thing I do want to mention here is height is actually a function of time, so I should probably write this as a function of time. So height as a function of time is actually equal to a negative 197 cosine of pi over 15 t plus 227. There you go. And you can test it out and see, but that is actually the function that represents a rider's height at any given moment on the London Eye. I made up the fact that they enter at a height of 30 feet, so I'm not 100% sure that's correct, but I know everything else is. As a final example, let's investigate some data. The table below lists the average monthly temperatures at Cosine River College in Sacramento, California. And we are going to build a sinusoidal model for this data. And the hint there is very important. Plotting these data points can be very helpful. Now, because we are now more advanced as a society and we have technology, I'm going to plot these using Desmos so that I can get a better visual. Because if I just try to plot these by hand, it's not going to work out. So let's go to Desmos. And I'm going to insert a table here. And the table will be January. The average temperature was 59, and February is 63, and March was 68. April 73. So I'll just quickly do this. There we go. Now, those points should be plotted, but unfortunately they're just too high. So let me adjust this table a little bit. And not table, I meant let me adjust the graph a little bit. And you can see, here's the data points. It dips kind of low. It does have a little bit of a sinusoidal shape to it, but really I'm more interested in trying to figure out what the maximums and minimums are and make sure that it's somewhat symmetric. So month 7, 93, month 1, 59. I think that's pretty fair to use those two. Hopefully it gets back down to that 59 in month 12. So that's what I'm going to use for our data set. We'll go from using 1 comma 59 and 7 comma 93. All right. So let's do this. And let's see here. First of all, these are minimums and maximums. So if you saw from the data, it went sort of like this. So it's an upside down, temperature function is equal to an upside down cosine function. Bx plus c plus d. And it's to find out what the amplitude is, we're going to find the midline here and the distance between the highest high to the midline or the lowest low to the midline. It doesn't actually matter. The midline is going to be at the average of 59 and 93. 59 and 93. It's basically the halfway point between those two values. So if we compute that, that's going to be 76. And so our amplitude, I'm going to actually do, so this is, let's just say 76 right here. I want to find the distance between that midline and either the maximum or the minimum. I'm going to go with the minimum because the math is easier. So the amplitude is 76 minus the 59, which is 17. So our temperature model is negative 17 cosine of bx plus c plus d. Now remember, b is the period, and obviously the period's 12 here. B is not the period. If I said that, I did not mean that. B is associated with the period. The period is 12 because it's 12 months in a year, and that's 2 pi over b. Man, I've been lecturing for too long. So I'm going to multiply both sides by b and divide both sides by 12, and I get pi over 6. So that'll be a negative 17 cosine of pi over 6 x plus c plus d. Now, we do have a phase shift here. We started our graph at time 1. That's our phase shift. So our phase shift is equal to 1, and that's supposed to be negative c over b. Well, let's go ahead and insert b in there, pi over 6. I'll multiply both sides by pi over 6. And now multiply both sides by negative 1. And that's what we get, negative pi over 6. So I'm going to insert that in for c, negative 17 cosine of pi over 6 x minus pi over 6. Plus d, and d is where our midline is, which we said was 76. So let's go ahead and see how this looks. And you got to love it when your models the data pretty decently, and it does. So that works very nicely. Of course, we only picked 2 points, And those 2 points might not have been the best. I could have picked maybe 8,92, but I don't think that's actually a good point to pick. I think this one actually works fairly nicely. Yeah, month 13, which is January again, you're back to 59 degrees, which is right there. So it does model okay. It's a good predictive model. And by the way, those are the average temperatures over the last 20 years in Sacramento. So it'll model this for 20 years. I mean, yeah, obviously, in any given month, it can be slightly different or significantly different. But generally speaking, over time, averages will be around here. All right. So those are the applications that I would probably recommend being good with. And I hope that you learned something from this series. If you have any questions, leave them in the comments in any of my videos. Not random videos, just a video that you're watching. If you have a question, I do answer them. Otherwise, thank you for watching.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.